Okay, so part two of our discussion today is about a different type of musical instrument that I brought to show you. What you're looking at here is just a plastic column. It's filled with water up to a certain level, which you probably can't see, but this is the water level right now. And this is open at the top, and that water in the cylinder actually is connected to a little bucket over here, and the water is at the same level in both right now. They're connected by a hose. But I can adjust this bucket. I can move it up and down. And by doing that, I'll be able to change the amount of air that's open here. All right, I'll be able to lengthen that column of air. So this is analogous to a wind instrument, all right, where, for example, in the trombone, we have a column of air, and we can make waves in that air that will come down, bounce off. In this case, it's closed at one end by the water, so they'll bounce off of the closed end. They'll go back up, and actually waves will bounce off partly when they reach the open end. Partly they come out, but also they partly reflect. So waves can bounce back and forth in here between those two ends, creating a standing wave if we have the right frequency to match the length of that tube, right? So this open air column has multiple resonant frequencies. We're going to try to make a resonance in this air column here and use that to do something, as you'll see. So imagine this is like a Coke bottle or something where you can blow across the top and produce a tone. Instead of blowing across the top, though, what I've got is a little speaker connected to my function generator, and I'm going to go ahead and turn that on, and you can see that the frequency on the function generator right now is set to 400. That's 400 hertz. So you're going to hear a tone coming from the speaker. I'm going to not turn it up very loud yet. Okay, so that's a 400 hertz frequency. All right, now what I'm going to do, I'm going to lower that water, and I want you to listen to the sound you can hear as the water level changes. Okay. I'm hoping that you were able to hear that when the water level passed a particular point, which was right here, the sound that you were hearing should have gotten noticeably louder. We just made a resonance, all right? So the frequency of 400 hertz, that sound wave produced by the speaker, was bouncing back and forth in here, and when the length of this air column got to be the right length, we could get a constructive interference between the waves passing in different directions. A resonance, in other words. And a resonance has the characteristic that the amplitude got big, so you should have heard a louder sound. All right, I'm going to measure one more thing here. I'm going to measure the distance from the end of the tube to the point at which the resonance happened. All right, that's pretty close to 20 centimeters, right, from the top of the tube to the mark where the water column was when the resonance happened. All right, I'm going to get these out of the way. So now we're going to use the short experiment that we just did. When we analyze standing waves or resonances, we always start by drawing snapshot graphs. So I want you to imagine, how was the air inside that open column? How was that air vibrating? Remember, sound waves are longitudinal waves. So the air is actually, little pieces of air inside the tube are actually vibrating in this direction up and down, parallel to the direction that the wave is traveling. But we're going to represent that longitudinal wave on the same kind of snapshot diagram that we do for transverse waves, like waves on strings and so on. So if the air column is open at the top, and there's nothing preventing the air from moving longitudinally at the top. The air is not tied onto anything or prevented from moving. we would say that the air displacement must have an antinode there because the air is free to move. Similarly, at the bottom of the column where the water was, the air is not free to move up and down because there's a barrier. So the air displacement would have a node at the lower end of this. Now if you're reading the night textbook makes snapshot graphs of longitudinal waves of sound. They're not displacement versus position graphs. Those are air pressure versus position graphs. And what you'll see in night is that the pressure actually has a node here because the pressure at the open end must remain atmospheric pressure. And the pressure has an antinode at the water because pressure can push harder on the water and reach a maximum. So I'm going to draw air displacement versus position graphs. They're going to look the opposite of what night textbook shows because that's a pressure position graph. Okay? So for my graph, we have snapshots of what that air displacement is going to look like. One more time, there's going to be a node at the bottom because the air is not free to move. It's blocked by the water. And an antinode at the top. And I'm going to assume, I could be wrong, but I'm going to assume that the particular resonance that we found was in fact the fundamental resonance, the fundamental standing wave for an air column. Fundamental means it's the longest wavelength. It has the fewest nodes and antinodes. And that would look like this if I draw a snapshot. Here's a second snapshot at an instant later. Remember, we're trying to represent longitudinal motion on a picture that kind of makes it look like the air is moving in a transverse pattern, but it's not. This is just representing that the air vibrates a lot in and out of the tube at the top and not at all here. So this is an antinode. Okay, so we made some measurements. We measured the frequency, 400 hertz. We measured the length of this column, and it was about 0.2 meters or 20 centimeters. And as you can see, this is not a complete wavelength. This is actually, the length here would be only 1/4 of a wavelength. The wavelength of sound that you were hearing was actually 4 times the length of this. All right? Well, if we know the wavelength and we know the frequency of that sound, we can make another simple calculation to find the speed of that wave, which is always the product of the frequency and the wavelength. Well, if I multiply 400 hertz by 4 times 20 centimeters is 0.8 meters, I get 320 meters per second for the speed of that wave. Well, that number should make sense because we know that this was a sound wave, and sound waves in air travel at around 330, 340 meters per second. So the experiment that we just did is also a simple way to estimate the speed of sound waves in a material by knowing the frequency of the wave that's causing the resonance and the wavelength of the resonance that you make. And you'll be using a similar technique to find the speed of waves in Lab C6, Part 6.